last speaker for this first session is Nikos Tzevelekos from Queen Mary. And the title of the talk is Fully Abstract Normal Form Bisimulation for Call-by-Value PCF.
Sorry, Okay. Yeah, thanks. Thanks for the introduction. So I will be presenting joint work with Vasileios Koutavas and Yu Yang Ling from Trinity College Dublin. This is a work we presented in LICS last year, and it's about the same theme of normal form bisimulation in a call-by-value setting. In this case, it's call-by-value PCF, so it's a type Turing complete language. Okay, so just a few words about program equivalence. Program equivalence is a problem of checking whether two programs have the same behavior under every context. So P1 and P2 programs are equivalent. If for every context C, if I put P1 in C and this terminates, then also P2 in C terminates and the other way around. So no context can distinguish between P1 and P0. P1 and P2. So for example, here I have two examples. I have a function that takes as input as another function, f, and then returns 0. That would be program P0. And P1 takes a function as input f. It applies f to the empty input. It takes back a value, an integer. And then it does the same thing again. And then compares the two results. And then if the results are the same, it returns 0. Otherwise, it returns another number. And then we can see that well, if f were to terminate, then depending on whether f can, or the context can remember how many times f would be called, then these two calls will return 0 twice, return the same number, and then will return 0. Otherwise, they would return 42. On the other hand, in P2, we have a function, a program that takes a function as input, again, f. It applies f to the empty input. And then whatever this returns, it doesn't matter, because then we get true, so then we just return 0. So one question we may ask is, are these programs equivalent? As already said, P0 and P1 are not equivalent because, for instance, f can diverge, and therefore this would distinguish between the two. P1 and P2 are not equivalent, again, because maybe the context can remember how many times f is called. And here is how we can distinguish between these two terms. So there is a context, the first context, you see you define this function bot that just diverges, and if you give this diverging function as input, it distinguishes between the two contexts, the two programs, whereas P1 and P2 can be distinguished by this other context, which has some memory, this reference that is initialized to 0. And then the first time you call it, the reference is 0. So it will just increase the reference and return 1. The second time you call this function, it will remember that the reference has been increased. So it will go to the else case and then diverge. So this context here would distinguish because in the first case it would diverge, the second ones would not diverge. Now, what if the only effect we had in the language was divergence? So what if the language was pure? And in this case, we have that the two first programs are inequivalent, the second two would be equivalent, because in a functional setting, you have no memory of how many times f is called. So if you call f once, or if you call it 2 or 3 or 4 times, it's the same thing. It will always return the same thing, and therefore the two programs are equivalent, P1 and P2. And now this is something that is very maybe easy to talk about intuitively. It's very hard, though, to talk about formally, to have a model, a system that allows you to prove this sort of equivalences. And in very, very short, very briefly, this is the contribution of this work, is a fully abstract normal form bisimulation for the language PCF, call-by-value PCF. This is a Turing complete language, call-by-value with integers and basic arithmetic. So what we formalized, what we did is we introduced this label transition system Here I have an example of a rule just to show you that it's a label transition system. It's not that the rule at this stage is not so important. But here somewhere you have terms, and then you reduce terms, and then you produce some labels. While you do that, there is a lot of environment. As you can see, there are many, many contexts for environment. So there's a lot of environment. This is configurations in this LTS. But you can reduce terms. You can also reduce terms that are open, that have open functions, or the higher order. They take functions as input, so they then become open, and so on. And these moves, these transitions you make are important because they have special labels. And then based on these labels, you define a bisimulation, so a notion of bisimulation, which is here at the bottom. So we say the denotation of P1, so the traces you get out of the LTS are in bisimulation, or the traces get out of P2. And we prove that the P1 and P2 are contextual equivalent if and only if they are bisimilar in this very special form of bisimulation. And we were also, because this bisimulation can be built a bit on the fly, you can build a model checker, so a bounded model checker that tries to see if it can distinguish between the two terms on the fly. And then sometimes it can even say that, well, these terms are equivalent because I have built a full bisimulation. And this is a tool that we, if you go in this link, you can find. Okay? All right. So so that was briefly an overview of the whole contribution. I will go in a little bit of detail just to give you an idea of what how this is achieved. Some introductions. So some of this we have already had in the previous talk, maybe with a slightly different take, but it's the same story basically. Is about contextual equivalence and normal form bisimulation. And here I focus on the language PCF because, well, PCF is the language that this paper is about. This was introduced in 1977 by Plotkin, who also introduced the full abstraction problem. So it was also introduced by Binler in the same year. Plotkin also produced a denotational model for PCF, and he showed that the model is not fully abstract. So what is full abstraction? Full abstraction is can we find a model? So two programs are contextually equivalent if and only if they're equivalent or the same in the model. So this here says the denotation of P1 is equal to the denotation of P2 if and only if they are equivalent. And now this thing that continuous functions did not work led to a lot of a series of research trying to constrain functions. Functions are too extensional in a sense. They can do behaviors that the programs cannot do, and that means that two programs may be equivalent, but not equivalent in the model because the model has a lot of objects, a lot of inputs that are not really implementable. On the other hand, most models you have that if two programs are equivalent in the model, they are also contextual equivalence. And then works try to take out behaviors of from functions to make them correspond to actual programs. Until in the early 90s, in three independent works, there was this introduction of games as a paradigm to model computation. And the idea is that you put a bit of more structure inside your functions, so you have these moves, these games. And doing that, you were able to show that you can have fully abstract models where basically two programs are equivalent, contextually equivalent, if and only if they are equivalent in the model. So we don't get equality in the model, we get equivalence in the sense that, well, the two terms cannot be distinguished in the model. There's no strategy you can play these programs against that can distinguish between them. And actually these results were based on definability, that in the model, every strategy that you have, so every element in the model is actually definable. There is a term corresponding to it. And this result was very important because there was it was kind of the start of game semantics for programming language, or like one of the starts. But it's an indirect model because here we don't have equality, we have equivalence. So basically we have transferred the equivalence, the contextual equivalence from terms to the model, but still we have to reason about every possible environment the program can sit in. So, And then later on, in 2010, there was a paper by Churchill and McCaskey that said, well, if we take the fully abstract model of PCF and we massage it a bit, we can extract information, we can extract these sets of obvious. This is a very technical term, but it says that don't look at the whole game, but just very specific parts of the game and put them together in sets, and this gives you a direct model. Two programs are equivalent if and only if they have the same denotation. Now, the model is a bit kind of, well, not peculiar. It's very game semantic, so it uses a lot of jargon from game semantics, but it exactly captures what we want, a direct model. On the other hand, in normal form Bisimulation, there has been a lot of work, starting from the work of St. George in the early 90s. The idea is we have LTSs, we know how to reduce terms that are closed. What happens when a term is open, or when you reach a lambda abstraction? So what do? Do you stop, or can you continue? And the idea is that you can continue, and you assume that in your lambda structures, you take inputs from the environment, and these inputs are names. You don't know what they are, but you know that if they are functions and you apply arguments to them, then you can make well, certain moves in the LTS that say, I want to apply this name. And in that case, in this LTS is for open terms, equivalence corresponds to bisimilarity. And that is what normal form Bisimulation is about. And it actually can capture contextual equivalence in a wide range of languages, but not to pure languages. So pure languages are again a problem because these LTSs are too discriminative for pure languages like PCF. And there is connection between normal form Bisimulation and game semantics, and for example, in this work by Lassen and Levy, it has been looked into. And in a sense, our work merges, again, is in the intersection of these two traditions in semantics. So here is the language that we examine. Is a functional language. It has types. It has some base types, and then functions and pairs or sequences. And then you can do the natural things. You can you have values, and values will be like constants, pairs. We have this fixed point so this is lambda abstraction with recursion. So you can have fixed point calculations. You also have these values that are external functions. So these are functions that you don't have in your program. They come from externally, so from the opponent, as it were, in game semantics parlance. And then you have application and then conditions. You also have evaluation context. This is a call by value language, so the evaluation contexts are called by value. This notion of external functions or names or abstract functions is very central in the semantics because it allows us to play the game between the term and the context it sits in. Okay? All right, so how can we build an LTS for terms like this or for open terms? The computation, the way the term behaves is modeled as a game between the term, which is the proponent, and its context, which is an opponent. So what can a term do? It can evaluate, so it can reduce, it can take an internal reduction step, E can go to E prime. In that case, in our LTS, we say that the configuration corresponding to E, and now I put dots because I don't want to put the full configuration. It's just I will be revealing what we have inside the configurations as we go on, moves to E prime. So E goes to E prime, and this is a tau move, it's an internal move. I have also put this P here because this is a configuration belonging to the term, to proponent, something happening internally. On the other hand, once a term reduces, well, either it reduces to a value, or it hits a function that it doesn't have the code for, so an external function, so these abstract functions I talked about. And in that case, the term can issue a move, a call, an external call, say, okay, I have this function alpha, it doesn't belong to me, so can we evaluate it with these arguments? So these are call moves. So for example, I have this evaluation context and I have alpha hitting a value v. And this will issue a call of alpha with v. And then you see that then next configuration has this O, which means belongs to opponent. So now this is the environment term to keep on playing in this game. If I hit a value v, then I can just return this v to the environment. And then the environment has to play, so opponent has to play. And here I have put in the configuration this vector v that is a bit different than this other v, so it's not a mistake in notation. What happens is this is the actual value I had, this is the abstraction of the value revealed to opponent, and this is the values that opponent can play from. In the next move, opponent will pick one of these values and call them. Or maybe they will return because opponent still needs to return something. So it's this, there's this sequence of calls and returns, and each time opponent has a restricted set of values they can call back from. And then I also need an evaluation stack because when I am in the middle of computation and I call opponent, this evaluation context E should not be lost, so I put it on a stack. So the abstracted version of the value v is just abstracts away the functions that I want to give to opponents. So instead of giving actual function, actual code, I give, I say, I have two functions, but I don't reveal them because I would be too extensional. And then from an opponent configuration, I can have a call. Again, opponent can call one of my functions, say the I function, or a return. And if there is a return, basically I fetch the last element, evaluation context, and I fill it with the value that opponent returned. And here in the configurations, I have revealed some more components. I have this T and M. So T is the current trace. So what moves have been produced? And M is the memory of the traces. And now these traces are not exactly the full trace of the computation. You see, it's very restricted because we want to imitate the way actual context would work in a functional language, where you don't, in a functional language, you don't have access to the full computation so far, only the one that is available in the textual closure that you have. So you have two calls of a function. For instance, the second call cannot see the inputs of the first call. And we use a special machinery to make sure that this the only restricts opponent to what they can actually see at a certain point. And this memory M makes sure that opponent is innocent, as it were. So if you call the same function twice with the same argument, it returns the same output. Here I had a slide about value abstractions. For instance, if you want to return 4 values, so you have this quadruple, you do keep the base values, and then for the 2 function values, you just return abstractions of them, so that opponent doesn't see the functions, but they know there are some functions there. Okay, so that was just a very brief highlight of how this would work. Now, what is the bisimulation that we defined? So the bisimulation is a bit, it's not exactly what you might expect. So if you have initial configurations when you start evaluating your term, so when can C2, so when can C2 simulate C1? When wherever C1 returns a value D prime, then C2 can return the same value and reach configurations that are still related. And then from there on, once we return values, opponent can call them, and then several things can happen, and eventually proponent would return. So we want to make sure that we match the calls and return. Only the high level, oops, the low level we don't need to match. So whenever there is a call return, opponent calls eventually will return, then the other terms should do the same, and we should also be related. Now, what you don't see here is that in the interaction in the game semantics, there are many internal moves. So there is a high-level call, and then several other moves happen. And these moves are hidden. They do not appear in this definition. Anyway, and then you reach configurations where the memory components, so the traces that you have gathered, they're also related. So in a sense, the simulating term, C2, has used a context that is less powerful than the simulated term. So this is what the second condition says. Anyway, and the result shows that the two terms are equivalent if and only if they're bisimilar in this term. The semantics is bisimilar in this way. Okay. I think I should be wrapping up, right? Okay, I have I had an example, but maybe I can just skip and go to the summary. So yeah, this is what we presented. There are more details, obviously, in the paper, and also you can also try the tool. So we devised a fully abstract normal form Bisimulation for PCF, for call by value PCF. What we have here, okay, we have this system. It's very nice, but it's a direct way to characterize equivalence, but it's still hard to prove equivalence. It's much easier, much more easy it's much easier to prove inequivalence, obviously, but you can prove that there are distinguishing traces, for instance. But to prove equivalence, you still need to build by simulations. We use up-to techniques to make this more feasible, but still it's hard, and this is something we work on. That's all. Thanks.
We have time for one or two. Yes.
Thank you. You mentioned at the end that inequivalence is obviously easier to prove because we just need to demonstrate a context. Does your technique or does your bisimulation process, does it provide a way of generating the contexts necessary?
Yeah, so you can... So the tool, for instance, that shows an equivalence, it can produce a trace, and then from that you can use definability to define a context. But we haven't implemented that. Yeah.
Thanks. So, does your method, or does your work rely on the sort of existing facts like congruence of applicative bisimulation or context lemma or something like that, or does it provide new ways of giving those results?
It's based it's based a lot on the work by Martin Churchill and Jim and Guy. So he takes the equivalence from there, and then it kind of tries to transform it, like take the result from there and transform it to this setting. So this is the main requirement. Basically, this is for completeness. For soundness, we use the standard techniques from most of the standard techniques from normal operational semantics, operational game semantics.
Okay, so you're using Howe's method.
No. So and then from standard operational game semantics, we would use.
From operational game. Okay.
Yeah, we use this like adequacy where you compose. So it's a different method that it was introduced, I think, by Jim Laird. Okay. Where you show composition externally and internally. Yeah, we can talk about this. Yeah.
Thanks.
Okay, thank you. It's probably best to stop there and go for the coffee break.